So our final speaker before the break is Vikram Kosa from ARM. He's a principal engineer. He's been spearheading initiatives in advanced formal methodology as well as hands-on deployment of formal methods across various roles and CPU designs at ARM's Austin Design Center since 2013. And the title of his talk is Pushing Forward the Frontiers of Formal in ARM CPUs.
Get this to work, sorry.
Sorry?
This isn't working.
Maybe you need that higher, that's all. Are you looking for the pointer?
No, just a clicker.
Yeah.
Okay. Perfect, thanks.
You'll need that otherwise.
I could just...
Okay.
All right, sorry guys. Hello everyone. So I'm gonna just outline I'm gonna cover a little bit of how we got formal into the mainstream and ARM CPU, talk about some present challenges, and look at kind of what the shape of the future looks like for CPU formal, and then conclude with some thoughts. So just quick background, we started somewhere around the early 2010s and it kind of sprung up in different sites, and we have CPU teams doing formal in around 6 locations. So in terms of how we got into the mainstream, some of the early hurdles, as I think these are sort of universally kind of experienced across the industry, designer engagement, getting buy-in from management, finding the right scope, finding the right ownership model between designers, verification teams, and formal engineers, getting the right kind of resourcing going, as well as defining some, clean criteria for what does it mean to succeed. So some key enablers, one of the things that we really pushed for was integrating formal into the kind of overall development flow. So we started out as a centralized team, but goal was to get formal out of its silo and kind of proactively engage with unit leads and just overall project workflow. What that meant was we needed to kind of embed formal engineers inside unit teams. It was harder than we thought it would be, but part of it was positioning formal as kind of an essential skill for all verification engineers. So the way that worked probably the best was the formal engineer goes in and owns both simulation and formal, and then as sort of opportunistically as formal shows value, migrate to a formal only test bench. The second aspect of this was how do we seek opportunities for left shift. Some of the early successes we had early on were basically some of the special formal flows that kind of played to formal strengths. One of the key ones was the data path verification using C2RTL, and we kind of created a sort of unique methodology using both C2RTL as well as theorem proving, which has been wildly successful. Clock gating verification using SEC, X-prop checking, and functional safety, etc. For FPV, I think the challenge was finding the right shaped test benches. So having the right balance of sort of feature complexity versus formal complexity. And as we found through trial and error, one of the critical factors for success was staying in sync with RTL development. That kind of yielded the most number of bugs throughout. What that also meant was having sort of a dedicated formal engineer that kind of eventually allows us to create like a formal only test bench we talked about. Number 3 was organizational support, having kind of management having like a longer term vision of staying invested, placing smart bets on kind of low hanging fruit, but also investing in tackling tougher challenges. So that the benefit of that was as we developed new techniques and flows, et cetera, they kind of helped all existing problems as well as future deployments. What also helped was having some special interest groups across the different teams to work on both technical problems and also kind of on strategy, best practices, and enable reuse. So what are some of our current challenges? One of the biggest ones most recently has been compute cost. I think we've heard about it in some earlier presentations too, that the amount of compute ARM kind of spends on verification. So that's no surprise there. I mean, the design feature complexity has grown, as well as the deployment surface. We're deploying formal and more things, and part of it's also sort of higher throughput requirements. We have shorter project cycles, reduced time to market for more segments served, and so formal's obviously no exception as we've grown. Some of the additional factors have been more environments, more users running formal, more design configurations, more specialized flows, as well as keep proliferating more bug hunting strategies and other proof strategies. So there's sort of three aspects in terms of solution space. One is sort of cluster based, kind of moving to the cloud, which kind of accommodates some peak demands. In some cases, also ring fencing using some lower, cheaper cost clusters to avoid sort of contention with other kinds of compute. So we've kind of been experimenting with both. The other aspect of the solutions for compute cost is kind of regression based. So there's sort of three buckets here. One is debug fitted regressions. Don't generate more fails than you have resources to debug. Again, kind of common sense, but it's important to kind of have enforced that. And then the second one, which is not very obvious, is property fitted regressions, which means if you run let's say a nightly on too many properties at once, you're spreading your resources too thin, which kind of undermines the whole point of it in coverage in general. So the idea is to find the right sized regression. And thirdly, also developing some clear metrics for what we care about in terms of what we want to optimize for a given run. And the answer may vary from run to run. So again, the next step was to create sort of benchmarks based off of these metrics. And so we can regress against, like anytime there's a new tool feature, et cetera, we can regress against what's the impact. And finally, there's sort of tool-supported solutions like proof caching, profiling, sort of hybrid flows where you run exhaustive proofs, and then have, based on some measure of stagnation detection, you kind of overlap it or follow it by bug hunting flows. And then also some ML-based optimizations, which we're going to try and exploit. The other biggest challenge is complexity. It's been sort of increasing, as I think that's been kind of the theme of some of the earlier presentations too. That's been increasing across the board. Even some of our lower power CPUs are adding more speculation by the day. So that's just that's kind of how it is right now. But in terms of complexity, I like to think of this as sort of two different buckets. One is sort of interface complexity and design complexity. They're related, but as you can see, the effect of this on formal test benches is slightly different. So what I mean by that is, in some cases, we wanted to test a complex feature at sort of a higher level of design hierarchy, which usually means a bigger DUT, and which typically has less interface complexity, but obviously more design complexity and places a higher burden on the tool. And then in the other case, you want to test something very small, the nice thing is you have a smaller DUT and the design is less complex. However, what tends to be the case, especially for CPUs, is the interface complexity blows up and it's pretty volatile. There's lots of timing changes, et cetera, that happen all the time. And that places a higher burden on the designer that's supporting that sort of low-level environment. So in terms of solutions, I think the biggest one is finding the right DUT to apply this on. So the ideal one would be something that has low enough design complexity and low enough interface complexity. And there are such units where things are pretty well defined, but you're at the right size. The other approach is to sort of limit stimulus or checker, both in terms of scope or lifetime. We have developed, we call stimulus limiting profiles, sort of more structured ones. We statically bucket them and use them. Narrow down the scope of checks in terms of case splitting, and in some cases bring up only test benches for sort of smaller subunits and not maintain them throughout the project lifecycle. And then there's the third kind of like the standard things we do for complexity, design mutations, abstraction models, initial value abstractions. What is the future shaping up to be? So we see is FPV is not going anywhere. We're continuing to proliferate. There's more environments, more kind of diversity in size, complexity. Also, in terms of increased areas of focus, regression efficiency, we're also looking at, we've been working on architecture-based kind of derived VIP in most cases sort of automatically. Liveness, that's been a source of pain at times. Functional safety, security, these are all going to be increasingly important. And also having some increased alignment in terms of efficiencies for things like front-end tools or triage or other flows, having a central formal team to kind of support those. So in terms of what directions, if we're trying to innovate to solve some of these problems, scalability, convergence, special flows methodologies, and new applications. So for scalability, we keep experimenting with new bug hunting flows, and those have improved over the years. We also look at things like trace profiling, where we look at mine interesting traces for states or inputs of interest, and then kind of replay those or explore nearby states. Things like property clumping, finding the right groups of properties to run together to exploit locality. Aggregating bounded proofs. In some cases, we run them in different cycles, and then having the way to put them back together to improve proof bounds. We also created a flow graph-based approach, which was presented back in 22. The idea here is to specify microarchitectural flows as event graphs, and then kind of generate safety and liveness properties based off of what's the legal hops or paths defined in those graphs. And also looking at sort of dynamically generating some of these stimulus limiting profiles based on some goals or end goals. In terms of convergence, one of the key areas of focus is sort of human-guided proof closure. There was a paper we published back in 21 about this, but this is an ongoing effort. The idea here is to kind of automate the generation of helpers, which is usually hard if you do it by traditional methods to kind of come up with helpers manually. We're trying to automate generation of these based on sort of a user-specified list of signals, and then proofs of these helpers can be used to improve convergence by, by induction for some of the harder properties. What goes hand in hand with this is sort of also structured proofs, where we have all these helpers, want to keep them integrated and also be able to break down proof across different case splits, et cetera, and have a way to kind of do all the bookkeeping for these. So that's quite helpful there. And also we have some using some techniques to kind of do some automatic case splitting and generating based on interesting variables. In terms of special flows methodologies, architectural specification-based flows, we have had a number of these developed over the years, but we're just trying to push them as things get more complex. They're running into limits. We're trying to innovate. So we have something called ISA formal, decoder, MMU, memory models. These are all areas where we're trying to generate sort of a VIP directly from the spec. Liveness and FSM deadlocks, we've had some special flows for those. XProp and clock gating. This is, again, these are well, tested flows and have been quite successful, but we also constantly looking for convergence and also some notion of coverage especially for, more complex designs. We're also investing in methodologies for making sure our abstraction models, et cetera, that we use in formal are safe. How do we qualify our checkers for completeness? Also looking at symbolic simulation lately. And of course, then there's new applications. Security, I think that this is a big one that's been on the horizon for the last few years. So this is primarily using sort of an information flow-based approach. And we've kind of explored some attacks and vulnerabilities, and we published that in 22 on some key attacks, Spectre version 1, Meltdown, Spoiler, and most recently, Spectre BHP. And these are also used to kind of verify some of the mitigations we put in place. One other recent area is multi-cycle path verification as well. So to conclude, formal, as we know, for as is true for most industries, no longer lives on the fringe. It's pretty much mainstream, or at least getting there. So what that has meant is the compute footprint has expanded, and you've got new challenges that are driven by, sort of competing demands of efficiency versus effectiveness, and plus all the increasing complexity of designs that we throw formal at, plus also some of the new areas we're applying formal in. So we got to keep innovating, reducing the compute cost and complexity, improving convergence, and sort of keep pushing the boundaries on new use cases. So I have.
Well, thank you, Vikram. We've got one question online, but we'll go to the audience first. So there's one question in the audience, please. Any others? We've got one. Yeah. Okay.
Hi, this is Bhaskar from Condor. Hi,
sorry, I can hear you.
Yeah.
This is Bhaskar from Condor Computing.
Okay. Hi.
I have a question. Can you please give some details about the symbolic simulation, the areas where you have been adapting?
Symbolic simulation?
Yeah.
This is something we're just getting into. And I think the primary use case for these is sort of data path and also looking at security. So these are all sort of commercial vendors coming up with their offerings.
Great, thank you. It's a huge effort. I could see the whole slides. Thank you.
Yeah.
The question online was regarding C2 RTL verification, right. and you have a flow for that internally?
So we use sort of a hybrid methodology, as I mentioned, one of the early slides. So the idea there is to do part of the kind of use C2 RTL against sort of a lower level model, and then we perform theorem proving against the actual spec.
Okay.
So that's it's kind of a hybrid methodology. So it actually eases the burden on the C2 RTL tool. So we don't have to deal with sort of complexity challenges there. But so the theorem proving part is it's a little more manual, but it's been quite successful.
Okay. Okay.
Yeah.
No more questions? None in the audience either? Okay.
All right.
So we'll go to our break, and then we'll be back in here in half an hour. But there's, again, 2 breakouts. So if you wanted to go to a breakout, there's Doulos, again, Doug Smith. He's looking at practical hacks for system Verilog coverage. And also there's a remote speaker on FPGA VHDL verification. That's Espen for EM logic. And in here, we got latest topics in verification, symbolic execution, fuzzing, and verification education. Okay. See you in half an hour. Thank you.